Hello, curious friend, and a very warm welcome to Deep Field channel. Tonight we are going to venture to the edge of everything that exists, to that place where the universe ends, or perhaps where it simply ceases to be what we know, and I promise to do this with such calm and gentleness that even infinity will feel like a good pillow. But before we embark on this journey to the end of all things, I would love to know in the comments from which corner of this wonderful little planet you are listening to me tonight. And if tiredness has arrived before the words, just leave a simple hello. This small gesture tells YouTube that this space is welcoming, that there is a community of curious minds gathering here to relax together. And this helps us bring even more people who need a quiet place to rest with science. If our journeys do you good, please also leave your like and subscribe to the channel. And for you who are already part of our family, my sincerest thanks for continuing to be here. Now, wherever you are, find a position that feels made for you. And if sleep comes to seek you, accept the invitation with gratitude. Let us begin. There is a question that almost every human being has asked at least once in their life, usually on a night with an open sky, lying down somewhere, looking up with that strange feeling of being simultaneously very small and part of something immense. The question is simple in form, but impossible to let go of once it enters the head. Where does the universe end? What exists there at that final edge, if an edge even exists? What lies beyond the beyond? And the most disconcerting thing of all, what does the word beyond mean when we speak of something that perhaps has no outside? You have probably felt this vertigo. It is not exactly fear, it is a philosophical dizziness. That sensation that thought has reached a glass wall and cannot cross it but also cannot stop trying. It is like trying to imagine what existed before time, or trying to see the back of your own head without a mirror. The human mind was built to navigate between trees, recognize faces, plan dinner. It was not made to contemplate infinity without stumbling. And yet, here we are, the species that insists on asking questions that do not have easy answers. What we are going to do together tonight throughout all parts of this journey is exactly that. Go there, calmly, with eyes closed and mind open. We will get as close as possible to the edge of the universe, using everything science has discovered, everything the brightest physicists and cosmologists in history have been able to map, measure, calculate, and intuit. And along the way, you will discover that the universe is much stranger, much vaster, and much more surprising than anything popular imagination usually constructs when it thinks of the word space. But let us start at the beginning. Or rather, let us start from where you are now, at this exact moment. While you breathe and feel the weight of your body, you are moving, not just rotating with the Earth around its own axis, which is already a speed of about 1,700 kilometers per hour for those living near the equator. You are also moving around the Sun in a smooth and immense arc that takes 365 days to complete, at a speed of approximately 107,000 kilometers per hour, and at the same time the Sun itself, dragging along with it you, the Earth, all the planets and everything else orbiting around it, is moving around the center of the Milky Way at a speed of approximately 800,000 kilometers per hour. And the entire Milky Way, with its 200 to 400 billion stars, is moving towards a point called the Great Attractor, which is a concentration of mass so gigantic that it pulls entire galaxies as if they were leaves in a river. And all of this is moving within a universe that is expanding in all directions at the same time. You are stationary in your bed, and you are traveling faster than anything the human mind can truly feel. This is the first great lesson about the universe. Stillness is a local illusion. Rest is a privilege of perspective, not a property of the cosmos. Now, to begin reaching the edge, we must first understand the stage. We need to understand the scale of what we are crossing. And here lies the greatest intellectual trap that exists when we think about the universe. We think we already know the size. We think that very large says something. It does not. It does not even come close. Let us use an analogy. Imagine you take a single cell from your body, a common cell, and place it in the center of a room. Now imagine that this cell grows until it is the size of a grain of sand. To maintain this proportion, your own body on the same scale would have to be the size of a mountain range several kilometers high. This difference in scale from a single microscopic cell to an entire human body is already disturbing. But the universe does something even more radical with our sense of proportion. The distance from the Earth to the Sun is called an astronomical unit. It is approximately 150 million kilometers. This is already a number that the human brain simply refuses to visualize truly. If you drove in a straight line at 100 kilometers per hour without stopping, it would take about 170 years to reach the Sun. But this distance, this huge astronomical unit, is just one step within our own solar system. The distance to the Oort cloud, which is the outermost region where objects are still gravitationally bound to the Sun, is about 50,000 astronomical units, 50,000 times the distance between the Earth and the Sun, and the nearest star to us, Proxima Centauri, is about 4.2 light-years away. A light-year is the distance light travels in one full year, traveling at about 300,000 kilometers per second. In a single second, light travels the distance of 7.5 laps around the Earth. In 1 year, it travels approximately 9.5 trillion kilometers. And the nearest star is more than 4 of these immense distances away. The Voyager 1 mission, the most distant probe from Earth ever launched by humans, which was launched almost 50 years ago and travels at about 61,000 kilometers per hour, would still take more than 73,000 years to reach Proxima Centauri if it were traveling in that direction, and we are still talking about our immediate galactic neighborhood. The Milky Way as a whole is about 100,000 light-years in diameter. It contains, as we mentioned, between 200 and 400 billion stars. Each of these stars may have planets. Each of these planets may have moons. The Milky Way by itself is already a territory so vast that the idea of exploring it entirely is science fiction of a level that not even the boldest science fiction usually treats seriously. But the Milky Way is not alone either. It is part of a local group of galaxies that includes the Andromeda Galaxy, the nearest galaxy of similar level to ours, which is about 2.5 million light-years away. The local group has more than 50 known galaxies, and this group in turn is part of the Virgo supercluster, also called Laniakea, which was mapped with greater precision only in 2014. Laniakea contains more than 100,000 galaxies and extends over 500 million light-years. 100,000 galaxies, each with hundreds of billions of stars. All of this within a single structure that is still just a small region of a much, much larger universe. The observable universe, which is the part we can see with the most powerful instruments humanity has ever built, has a radius of about 46 billion light-years. Not just 13.8 billion, which would be the age of the universe in years. 46 billion. This happens because the universe has been expanding the whole time, while the light that left the most distant regions was traveling in our direction. When it emitted this light, that region was much closer, but the space between us and it has been stretching during all the time it took for the light to reach us. So the source of this light now is much further away than the distance the light traveled. This is one of the first points where the universe begins to behave in a way that completely challenges everyday instincts. It is not that something is moving away from us in space, it is that space itself is growing. The distance between 2 points increases not because the points move away from each other, within a fixed container, but because the container itself, space, is dilating. Every cubic centimeter of vacuum is, at this exact moment, becoming slightly larger, and the further away a galaxy is, the more space exists between it and us, and therefore the faster this distance grows. There are galaxies in the observable universe that are moving away from us at speeds greater than the speed of light. This seems to contradict physics, which tells us that nothing can move faster than light. But it does not contradict because it is not the movement of an object within space, it is space itself expanding. The rule "nothing can be faster than light" applies to objects moving within space. Space itself does not have this limitation. This means that there is around us an invisible horizon, a limit beyond which no information will ever be able to reach us, a non-physical but absolutely real boundary, beyond which the universe exists but is permanently out of our contact because any light emitted from there is being carried away from us by the growth of space faster than it can reach us. This horizon is called the cosmological event horizon or Hubble horizon, and it defines the observable universe. Everything within it, under current conditions, can eventually send us a signal. Everything beyond it never will. We already see here a first rupture with the most common myth about the edge of the universe. Most people imagine a wall, something solid, a physical limit where space ends and absolute nothingness begins, like the end of a box, but the observable universe has no wall, it has a horizon. And just as the horizon you see when you look at the sea is not the end of the world, but only the limit of what your eyes can reach from where you are, the cosmological horizon is not necessarily the end of the universe. It is the end of the universe we can see. And what exists beyond what we can see? Here things get more interesting and more disturbing and more surprisingly humble for science, because the honest answer is, we do not know for sure, but we know some things. We know, for example, that the observable universe seems to be very similar in all directions. The temperature of the cosmic microwave background, which is the luminous echo of the Big Bang, is surprisingly uniform. Galaxies are distributed in filaments and clusters that follow similar patterns in all quadrants. It does not seem that we are near an edge. It seems that we are in the middle of something that extends far beyond what we see. The most accepted cosmological models today suggest that the total universe, including regions we will never be able to observe, is much larger than the observable universe. Some calculations suggest that it may be at least 250 times larger in each direction. Other models, based on the inflationary period that happened shortly after the Big Bang, suggest that the universe may be effectively infinite, or so large that the difference between much larger and infinite is academically irrelevant for any practical purpose. Inflation. This word will appear many times on this journey, and it is worth understanding it from the start. It is not price inflation, of course. It is a concept in cosmology that describes a period in the first instance of the universe, a fraction of a second after the Big Bang, in which space expanded at an extraordinary rate, much faster than the speed of light. In a fraction of a second smaller than anything we can easily name, the universe went from something smaller than an atom to something the size of a golf ball or larger. The numbers vary between models, but the central idea is this. There was a moment of growth so violent that the universe became smooth and uniform, like a ball of dough kneaded with force. The original irregularities were stretched to scales so large that they became imperceptible locally. This is why the universe looks so homogeneous on large scales. This is why the temperature of the cosmic microwave background is almost equal in all directions, even though opposite regions of the sky would never have had time, without inflation, to exchange heat and balance themselves. Inflation elegantly solved several puzzles in cosmology, and at the same time created new ones, because the mechanism that generated it if it existed, is not completely understood. But let us return to the stage. You are lying on a planet that rotates around a medium-sized star, which is located on one of the ends of one of the spiral arms of a medium-sized barred galaxy, which is part of a local group of galaxies, which is part of a supercluster, which is part of a network of filaments and voids that constitutes the large-scale structure of the observable universe, which is only the portion of the universe accessible to us because of the speed of light and the age of the cosmos, and which probably represents a tiny slice of what really exists. You are a footnote within a footnote within a footnote, and yet you are aware of all this. You can contemplate your own insignificance with curiosity and even with a strange beauty. This in itself is one of the most remarkable things that exist in the universe we know. Now, before we move towards what really exists at that edge, before we dive into horizons, multiverse theories, the final destiny of the cosmos, and everything else that is to come, there is a question worth leaving hanging in the air with you as sleep begins to arrive, a question that will guide the entire second part of this journey. If the universe is so immense, so active, so structured in galaxies and filaments and clusters that move and organize and follow precise patterns, where does the energy that animates all this come from? Where does the energy that animates all this come from? The question seems simple when spoken aloud, but it carries within it a weight that few allow themselves to feel completely. It is a question that human beings have asked in different ways throughout their entire conscious existence, using different words in different languages, in times when the starry sky was the only available book and contemplation was the only form of research. And even today, with telescopes that see galaxies at incomprehensible distances and particle accelerators that reproduce conditions from the beginning of the cosmos, the question remains one of the deepest that physics tries to answer with honesty. Imagine for a moment that you are holding a compressed spring between your fingers. While it is compressed, it seems inert, quiet, with nothing happening. But there is something stored there, something that has not yet manifested as movement, but that is present in the very configuration of the object, in the tension between its coils, in the resistance you feel in your fingers. When you release it, everything that was stored converts into action, into vibration, into heat, into sound. Nothing was created from nothing. Nothing disappeared to nowhere. What was potential became kinetic, and the universe remained exactly as full as it was before, only reorganized. This principle, which seems trivial when applied to a spring, is actually one of the most fundamental pillars of physical reality. The universe does not create or destroy energy. It transforms it, it redistributes it, it hides it in forms that sometimes take us decades to recognize. The question of where the energy comes from that moves galaxies, that lights stars, that keeps the universe structured and alive, therefore, is not a question about creation from emptiness. It is a question about inheritance, about what existed before and what was passed on in increasingly complex forms until it reached the cosmos we can observe today. In the beginning, if that word has any meaning applied to an event that inaugurated time itself, there was a density of energy, absolutely unimaginable, concentrated in a state that our equations describe, but that our minds cannot visualize without distortion. There was no space around, because space had not yet expanded. There was no time before, because time is a property that emerged along with space and with matter. What existed was a singularity of potential, a state of maximum compression that carried within it all the energy you see today, in the form of stars, planets, cosmic radiation, movement of galaxies, gravitational waves, and in the form of yourself, thinking about this as the night advances. This initial potential began to unfold. The cosmos expanded, and as it expanded, energy was distributing, differentiating, assuming distinct forms. Part of it became matter, following the relationship that Albert Einstein formulated in an equation that is probably the most famous in human history, the one that says that energy and mass are the same thing expressed in different ways, separated by a factor that is the square of the speed of light, a number so colossal that a tiny amount of matter holds within itself an absurd amount of latent energy. This equivalence is not a metaphor. It is a literal statement about the nature of reality. What you call matter is energy structured in a specific way, and what you call energy is matter awaiting reorganization. Einstein arrived at this conclusion through a path that mixed philosophical intuition with mathematical rigor. He was dissatisfied with Newtonian mechanics not because it was wrong within its domain, but because it seemed incomplete. Newton had described a universe of forces that acted instantaneously at arbitrary distances, a physics that worked perfectly for planets and apples, but that began to creak when confronted with phenomena involving light and extreme speeds. Einstein realized that the problem was deeper than a simple adjustment of equations. It was necessary to rethink what it means to exist in space and time. In 1905, a year that physicists usually call the miracle year, Einstein published 4 articles that each alone would have guaranteed his eternal fame. One explained the Brownian motion of tiny particles in fluids, confirming the real existence of atoms in a way that ended decades of debate. Another explained the photoelectric effect, showing that light behaved not only as a wave but as discrete packets of energy, which later earned him the Nobel Prize and paved the way for quantum mechanics. A third established the foundations of special relativity, revolutionizing the understanding of space and time. And the fourth derived the equivalence between mass and energy, that relationship that today every child learns before even understanding what it implies. What Einstein did was not just elegant mathematics, it was a complete reorganization of how physics understands what exists. Before him, energy and matter were separate categories coming from different boxes. After him, they became 2 aspects of the same underlying reality, like water and ice being the same compound in different states. This conceptual unification opened doors that we are still crossing today, including the understanding of how the sun shines, how atomic bombs release so much energy, and how the primitive universe was capable of generating all the matter that today forms galaxies from an initial state dominated by pure radiation. The sun is perhaps the best local example of how this energetic heritage of the primitive cosmos manifests in a continuous and visible way. In the core of the sun, where the pressure is so extreme that it surpasses any condition we can artificially recreate on Earth for prolonged periods, hydrogen nuclei are compressed with enough force to overcome the electrical repulsion between their positive charges and fuse into helium. This nuclear fusion process releases energy because the resulting helium has a slightly lower mass than the sum of the hydrogens that formed it. This difference in mass, which seems trivial, is converted into energy following exactly Einstein's equation. And since the speed of light squared is an enormous factor, even a tiny difference in mass produces an amount of energy that sustains the combustion of a star for billions of years. Every second, the sun converts about 4 million tons of mass into pure energy. 4 million tons per second for billions of years. And even so, the sun has enough mass to continue shining for a few more billion years before exhausting its nuclear hydrogen. This gives an idea of the scale of the equivalence between mass and energy, of how immense the energy reservoir contained in matter that seems solid and permanent is. The stone you step on, the iron in your blood, the calcium in your bones, all hold within themselves an energy that, if released in a manner analogous to solar fusion, would be capable of powering entire civilizations indefinitely. But the source of energy that sustains the sun is not the final answer to the question of where the energy of the universe comes from. It is just one step in a chain that goes back to the beginning of everything. The hydrogen that fuels the sun was formed in the first minutes after the beginning of the cosmos, when the temperature had dropped enough for protons and neutrons to combine into light atomic nuclei in a process that physicists call primordial nucleosynthesis. Before that, there were only quarks and gluons in a soup too hot to organize. The organization itself, the simple fact that particles could join and form stable structures, represented a dissipation of energy from the initial concentrated state to progressively colder and more organized states. There is a law that governs this process of dissipation, and it is so fundamental that some physicists argue it is the most important law in the universe, more central than gravity, more essential than electricity. This law says that the total entropy of an isolated system never decreases. Entropy is a measure of disorder, or more precisely, of how many different ways a system can be organized without its macroscopic properties changing. A cup of hot water has low entropy compared to a mixture of hot and cold water that has just been stirred, because the separation between hot and cold represents a type of organization that demands energy to be maintained and that tends to disappear spontaneously over time. The second law of thermodynamics, which is the formal name of this principle, was formulated throughout the 19th century by thinkers like Sadi Carnot, Rudolf Clausius, and Ludwig Boltzmann, each arriving at it by different paths and with distinct emphasis. Carnot was interested in the efficiency of steam engines, those noisy and powerful contraptions that were transforming the industrial world around him. He realized that no machine could convert heat into work with perfect efficiency, that there was always an inevitable loss, and that this loss was not the result of bad engineering, but of a deeper principle about how energy behaves in the universe. Clausius formalized this in mathematical language and introduced the concept of entropy as a measurable quantity. Boltzmann connected entropy with statistics, showing that the tendency towards increased disorder is not a magical law imposed from outside, but a natural consequence of probability. There are many more ways for a system to be disordered than ordered. Therefore, systems tend to disequilibrium spontaneously because disequilibrium is statistically overwhelming. Boltzmann paid a high personal price for defending these ideas. At the end of the 19th century, many physicists still resisted the idea that matter was composed of atoms, and Boltzmann's statistical theory depended fundamentally on this premise. He was attacked, ridiculed by prominent colleagues, and fell into a severe depression that accompanied the last years of his life. In 1906, he took his own life during a vacation trip with his family. With bitter historical irony, definitive evidence of the existence of atoms would be published by Einstein just 1 year later, posthumously validating decades of Boltzmann's work. The cosmos owes him a huge debt, and the epitaph on his tomb in Vienna carries an equation that is the synthesis of his most enduring work. The second law not only governs steam engines, it governs the fate of stars, the formation of galaxies, the possibility of life, and the final destiny of the universe. It is because the entropy of the primitive universe was extraordinarily low that there was so much potential available to dissipate in useful forms over time. Stars exist because cold and diffuse matter collapses gravitationally into dense and hot objects, and this collapse increases the total entropy of the system, transforming gravitational potential energy into heat and radiation. Planets exist because the process of stellar formation leaves behind disks of material that aggregate and organize locally, even while the global entropy of the system grows. Life exists because organisms are extraordinarily efficient machines at capturing low-entropy energy, such as sunlight, and dissipating high-entropy energy, such as body heat, while temporarily maintaining very low internal entropy, which is what we call biological order. You exist because the sun is at a distance and temperature such that its light reaches Earth with sufficiently low entropy to be captured by photosynthesis, which feeds food chains that eventually sustain the complexity of your body. You are an entropy dissipator, a temporary channel through which the energetic potential of the primitive cosmos flows towards final equilibrium. This sounds reductionist only if you insist on seeing reduction where there is, in fact, revelation. The complexity you experience as consciousness and curiosity is the product of billions of years of energy flow following laws that are elegant, inevitable, and profoundly beautiful. There is another law that needs to be felt before it is named. Think of a ball rolling on a flat and perfectly smooth surface, without friction, without air, without anything to disturb it. It continues rolling. It does not need a continuous push. It does not need an external source of energy. It does not need a cause keeping it active for the effect to persist. Movement is a condition that maintains itself in the absence of interference. Now think of the opposite, a ball that suddenly starts moving without anything having pushed it. This does not happen. Movement requires an initial cause, a change in the state of rest provoked by something external. This perception, which seems obvious when stated like this, took centuries to be formalized correctly because everyday experience is deceptive. In the world we live in, everything that moves eventually stops because of friction and air resistance. This created for millennia the intuition that movement is the condition that needs explanation, that something in motion needs a continuous cause to continue in motion. It was Galileo Galilei who began to suspect that this intuition was wrong, conducting experiments with inclined planes and rolling spheres, trying to extract from real situations the ideal physics that existed beneath them. And it was Isaac Newton who finally formulated the law of inertia with precision. An object at rest remains at rest, and an object in motion remains in motion in a straight line and constant velocity unless a force acts upon it. Newton built on this foundation an entire system of mechanics that described the movement of planets with a precision that was considered miraculous by his contemporaries. The law of universal gravitation, which stated that any two bodies attract each other with a force proportional to the product of their masses and inversely proportional to the square of the distance between them, unified terrestrial and celestial physics in a way that transformed humanity's relationship with the cosmos. Suddenly, the same force that made an apple fall was the one that kept the moon in orbit and governed the movement of the planets. The universe was subject to measurable laws, and these laws were the same everywhere. Newton's contribution was so monumental that his mechanics governed scientific thought for more than 2 centuries, almost without contestation. But there were tensions, places where the equations produced results that did not fit completely with observation. The orbit of Mercury, for example, precessed in a slightly different way than Newtonian gravitation predicted. The discrepancy was tiny, but it was there, resisting attempts at explanation through undetected planets or known perturbations. It waited patiently for a better theory. This better theory arrived with Einstein again, this time in the form of general relativity, published in 1915 after years of intense work that Einstein later described as the most demanding and fruitful period of his life. General relativity reinterpreted gravity not as a force acting at a distance, as Newton had conceived, but as a curvature of space-time itself caused by the presence of mass and energy. Massive bodies deform the fabric of space-time around them like a heavy ball deforms a stretched elastic fabric. Other bodies, moving through this curved space-time, follow the straightest possible trajectories in a geometry that is not flat, and these trajectories are what we call orbits. The image of the ball on an elastic fabric is imperfect like every analogy because the elastic fabric needs gravity to deform. creating a circularity that reality does not have. But it captures something true, the idea that the geometry of space is not a fixed stage upon which events happen, but an active participant that is shaped by what it contains, and that in turn shapes how things move. Space and time are not containers. They are part of the content of the universe, intertwined with matter and energy in ways that have so far produced predictions confirmed by every experimental test submitted to them, including the detection of gravitational waves in 2015, a result that would have delighted Einstein beyond measure. The imbalance that makes the universe work, that makes stars be born and explode and scatter their elements, that makes galaxies collide and merge and form larger structures, that makes black holes grow and quasars illuminate distant cosmic eras. This imbalance has a technical name but a simple essence. It is the difference between the state in which the cosmos finds itself and the state of maximum equilibrium that the second law inevitably pushes towards. As long as this difference exists, as long as there are temperature gradients, mass concentrations, pressure differences, asymmetries of any kind between regions of the universe, there will be energy flow, there will be movement, there will be process, there will be, in a word, universe. The cosmos is constantly trying to reach an equilibrium that it never completely achieves because the expansion of space itself continues creating new conditions before the old ones can resolve. It is like trying to fill a bucket that grows faster than the water entering. Every time a local system reaches something close to equilibrium, the universe around is already larger and colder and more dispersed than it was before, creating new gradients, new opportunities for energy flow, new stages for complexity to emerge briefly before dissolving again. It is within this context that something happens that we can observe in remarkable detail right here, in our immediate cosmic neighborhood. A cloud of interstellar gas and dust spread over light years of almost empty space begins to contract. The cause may be the shock wave of a nearby supernova or simply a random density fluctuation that gains enough mass for gravity to take over. Contraction compresses the gas, and compression heats the center of the cloud. Heat creates pressure, and pressure resists contraction. For a time, there is a delicate balance between gravity pulling inward and gas pressure pushing outward. As the center cools by radiating heat into space, the balance shifts in favor of gravity. Contraction continues. The center heats up more, pressure rises, but gravity keeps up. If the cloud has enough mass, the center will eventually reach the temperature at which hydrogen begins to fuse into helium. At this moment, a new source of energy enters the scene, nuclear fusion, providing enough pressure to definitively balance gravity and stabilize the object in a state that can last billions of years. A star was born. It shines because it is dissipating potential energy, converting mass into light and heat, illuminating the space around and heating any planet circulating in its vicinity. It is a channel through which the energetic imbalance of the primitive cosmos flows towards the equilibrium that the second law demands. When this star exhausts its nuclear fuel, the balance collapses once again. Gravity wins. The core contracts catastrophically in a matter of seconds, releasing in an instant more energy than the star emitted in its entire life, and the outer layers are expelled in an explosion that scatters into interstellar space all the elements that the star synthesized during its existence: carbon, oxygen, iron, nitrogen, calcium, and dozens of others. This material spreads over light years, mixes with interstellar gas, and eventually may participate in the formation of a new cloud that may contract and form a new star with a system of planets around it. What has just been described in a single location, in a single gas cloud in a single galaxy, happens on scales that the human mind does not process intuitively. Our galaxy alone contains hundreds of billions of stars in different stages of this cycle. The observable universe contains hundreds of billions of galaxies. In each of them, at every instant, clouds collapse, stars are born and die, explosions seed interstellar space with the elements of life, new planetary systems form from the material of previous generations of stars. The same local mechanism, repeating itself in variations on the same fundamental theme on scale after scale after scale. What happens when this mechanism repeats millions of times, billions of times in all galaxies throughout all cosmic time? When the gaze moves away from the individual and begins to contemplate the whole, something unexpected emerges. Not the chaos that would be reasonable to expect from a universe so vast and so old, but an architecture, a geometry that no star decided to build, that no gas cloud planned to inhabit, that no supernova explosion conspired to create. An order that was born spontaneously from the repetition of simple processes on scales that overlap each other like layers of an infinitely complex fabric. Galaxies, which are already colossal structures in themselves, are not randomly distributed through space. If you could float above the entire observable universe and look down as if it were a map, you would not see points scattered uniformly like grains of salt on a dark surface. You would see filaments, you would see walls, you would see nodes of concentration where these filaments cross, and you would see immense voids where almost nothing exists. The universe in its maximum scale has the appearance of a web or of a sponge, or of something that cosmologists called, with accidental poetic precision, the large cosmic structure. This web was not perceived immediately. For a long time, astronomers worked with catalogs of galaxies that seemed to simply enumerate objects without revealing the underlying pattern. It was like trying to understand the structure of a forest by looking at a single tree at a time, without ever moving far enough to see where the trees cluster and where the clearings open. The problem was one of scale and method. To see the web, it was necessary to map not only the position of galaxies in the plane of the sky, but also their distance, which meant measuring the redshifts of thousands and then tens of thousands and then hundreds of thousands of objects. In the 80s of the last century, a group of astronomers based at the Harvard-Smithsonian Center for Astrophysics began a systematic mapping project. Margaret Geller and John Huchra led an effort that seemed on the surface to be just a cataloging task. They measured the redshifts of galaxy after galaxy, building slices of the universe as if they were geologists analyzing rock strata. When they plotted the results of one of these slices, in a moment that Geller would later describe as one of the most surprising of her scientific career, the pattern that appeared on the computer screen did not look like anything they had expected. The galaxies were organized in a structure that became known as the stickman, an elongated and branched concentration that crossed the mapped slice as if it were a stylized human being with outstretched arms. The first reaction was to distrust the data. That looked too structured to be real, too geometric to be the work of cosmic chance. But the data were solid, and as larger maps were built over the following years, it became clear that the stickman was just a local fragment of an organization that repeated itself in all directions, on all scales, covering the entire observable universe. The filaments of this great web have lengths that reach hundreds of millions of light years. The walls, which are even flatter and more extensive concentrations of galaxies, can extend for billions of light years. The nodes where the filaments meet house the galaxy clusters, structures that contain hundreds or thousands of individual galaxies linked by mutual gravity, immersed in clouds of hot gas so extensive that they emit X-rays detectable from immense distances, and between the filaments and the walls and the nodes, the voids. Regions of space almost completely depopulated that can have diameters of 3 or 400 million light years, places where the density of matter is a tiny fraction of the cosmic average. The largest known void in the observable universe, called the Eridanus supervoid, or sometimes simply the Great Void, has an extent that defies any attempt at human visualization. It is not a void in the sense of having absolutely nothing, because perfect vacuum does not exist in the universe we know. But it is a region where the density of galaxies is so low compared to surrounding regions that it represents a statistical anomaly difficult to explain only by conventional gravitational dynamics. The formation of this large-scale structure has a history that goes back to the first instance of the universe. The small density fluctuations that existed in the primordial plasma, variations of 1 part in 100,000 in the material that filled the young cosmos, were the seed of everything that came after. Gravity amplified these fluctuations over time. The slightly denser regions attracted material from the slightly less dense regions. The concentrations grew, the voids deepened. What was an almost imperceptible texture in the young universe became progressively more pronounced, like folds in a fabric that contract as time passes. But gravity alone would not be enough to explain the specific geometry we observe. The shape of the filaments, the thickness of the walls, the characteristic size of the voids and nodes, all this depends on the exact mix of ingredients that make up the universe. And a large part of these ingredients is not common matter. It is not the type of matter that forms stars and planets and gas and ourselves. It is something that does not interact with light at all, something that only manifests gravitationally, something that physicists baptized as dark matter precisely because it does not emit, absorb, or reflect electromagnetic radiation of any kind. The existence of dark matter was not postulated by philosophical speculation. It was inferred from observations that did not make sense otherwise. Astronomer Vera Rubin, working with spectroscopist Kent Ford in the 70s, systematically mapped the rotation velocities of spiral galaxies. What they expected to find, based on the visible distribution of mass in these galaxies, was that stars in the outer regions rotated more slowly than stars closer to the center, just as the outer planets of the solar system orbit the Sun more slowly than the inner ones. What they found was the opposite. Stars in the outer regions of galaxies rotated with speeds as high as stars closer to the center, and often even faster. The rotation curves were flat where they should decline. There was only one coherent explanation. Galaxies are not just what we see. They are immersed in immense halos of invisible material that extend far beyond the luminous disk of stars and gas. It is this invisible mass that keeps the outer stars in orbits that would otherwise be too fast to be gravitationally stable. Rubin and Ford did not name this dark matter, but their observations were the most convincing and systematic evidence that the universe contains a massive component that completely escapes detection by any form of light. Decades of subsequent observations confirmed this in multiple independent ways. Gravitational lensing, the phenomenon by which gravity bends the paths of light, reveals concentrations of mass in places where no luminous object is visible. The dynamics of galaxy clusters, where individual galaxies move so rapidly that luminous mass alone would be insufficient to keep them gravitationally bound, points to the same conclusion. Computer simulations of the universe on a large scale only reproduce the observed cosmic web when including dark matter in specific proportions. Here, the large-scale organization begins to reveal its layers of depth. The cosmic web is not just a structure of galaxies, it is primarily a structure of dark matter, with luminous galaxies tracing the contours of the invisible mass distribution like illuminations on a framework that itself remains hidden. The filaments we see in visible light are the bright peaks of much more extensive dark matter filaments. The clusters are the nodes of a web whose majority is invisible. The voids are voids of both luminous matter and dark matter, and that is why they are so vast and so deep. When universe simulators build computer models of this large structure, starting with the initial conditions of the young universe and letting physics evolve over cosmic time, what emerges in the simulations is remarkably similar to what observations show. The Millennium Simulation Project, conducted at the beginning of the 21st century by Volker Springel and collaborators at the Max Planck Institute for Astrophysics, created a virtual box of universe containing more than 10 billion particles of dark matter and let this box evolve for more than 13 billion simulated years. The result was a cosmic web with filaments and nodes and voids that reproduced with remarkable fidelity the observational maps of real galaxies. What the simulations also revealed is the process by which individual galaxies form their own internal structures within this larger context. Galaxies do not form uniformly within dark matter halos. They form hierarchically, starting with smaller structures that progressively merge into larger structures over time. The first galaxies to form were small and irregular, building blocks that collided and merged to build the larger galaxies we see today. Spiral galaxies like the Milky Way and the Andromeda Galaxy are the products of billions of years of cosmic mergers and acquisitions. The spiral geometry of galaxies like ours has its own reasons for being. The flat disk that characterizes spiral galaxies is a consequence of the conservation of angular momentum. When a primordial gas cloud collapses to form a galaxy, any rotation that this cloud possesses is amplified as the material contracts, in the same way that an ice skater spins faster when pulling in their arms. The material cannot collapse equally in all directions because rotation resists collapse in the direction perpendicular to the axis. It collapses freely in the direction parallel to the axis, forming a disk. This is why galaxies with substantial angular momentum become rotating disks instead of spheres. The spiral arms that coil in these disks are themselves wave phenomena. They are not rigid structures of specific stars spinning together like the spokes of a wheel. They are density waves that propagate through the disk like sound waves in a gas, concentrations that move independently of the individual stars that pass through them. A star like the Sun enters a spiral arm, passes through it in a few million years, and then continues its orbit around the galactic center until it encounters the next arm. Spiral arms are zones of higher density where star formation is stimulated, where molecular clouds are compressed by pressure waves, and where the cycle of birth and death of stars that we described earlier happens with greater intensity. In the center of practically all massive galaxies that we examine with sufficient detail resides a supermassive black hole. Not the stellar mass black holes that are born from the death of massive stars, but objects with masses ranging from millions to billions of times the mass of the Sun. The black hole in the center of the Milky Way, called Sagittarius A, has a mass of approximately 4 million solar masses. The black hole in the center of the giant elliptical galaxy M87, whose historic image was captured by the Event Horizon Telescope in 2019, has a mass of more than 6 billion solar masses. The relationship between these central black holes and the galaxies that harbor them is one of the most surprising discoveries of modern astrophysics. The mass of the central black hole is correlated with properties of the host galaxy, particularly with the velocity dispersion of stars in the central bulge. This correlation suggests that the black hole and the galaxy co-evolved, that the growth of the black hole and the growth of the galaxy were somehow linked throughout cosmic history. When black holes actively accrete material, releasing enormous amounts of energy in the process, They can regulate star formation in the galaxy itself through winds and jets that expel the cold gas needed to make new stars. This feedback between central black holes and galaxies is one of the self-regulation mechanisms that keep galaxies within certain ranges of size and star formation rate. Galaxies that grow too much activate their central black holes, which then suppress further growth. Galaxies that stop forming stars have cooled and exhausted their gas supplies, partly because the energy released by black holes heated and expelled the gas that would feed new generations of stars. The universe has regulatory mechanisms that operate on scales of hundreds of thousands of light years. When galaxy clusters form in the nodes of the cosmic web, the individual galaxies within them experience an environment radically different from that of isolated field galaxies like ours. The space between galaxies in a cluster is filled with a very high-temperature gas, called intra-cluster plasma, which can reach temperatures of tens of millions of degrees and emits profusely in X-rays. Galaxies navigating through this hot plasma experience a drag pressure that can literally tear the cold gas from their disks, suppressing star formation and transforming active spiral galaxies into quiescent elliptical galaxies over billions of years. The process has a name that astrophysicists call ram pressure stripping, a reference to the metal ram used to knock down gates in ancient battles. The galaxy moves through the hot plasma of the cluster, and the gas from its spiral arms is swept back like the cape of someone running against the wind. The visible result are the so-called jellyfish galaxies, where the main stellar disk remains intact but long tails of ionized gas extend behind the galaxy in the direction opposite to movement, shining at specific wavelengths that reveal hydrogen and oxygen being ripped away. It is a form of slow-motion death, the transformation of an active star-forming galaxy into a quiescent relic. Galaxy clusters are the largest gravitationally bound systems in the universe. Above them in the hierarchy exist superclusters, collections of clusters that share regions of space but which are generally not gravitationally bound as a whole. The Virgo supercluster, of which the Milky Way is part, is a structure that extends over something around 110 million light-years. But even it is only a substructure of what has been identified as Laniakea, an even larger supercluster whose delimitation was mapped by R. Brent Tully and collaborators using the velocity fields of galaxies to determine gravitational attraction basins. The mapping of Laniakea represented a methodological shift. Instead of simply cataloging positions and distances, Tully and his team analyzed the movement patterns of galaxies, the deviations of their velocities from the general Hubble flow, to infer where gravity was pulling each of them. Just as the watershed of a river can be defined by where the water flows, a gravitational basin can be defined by where the galaxies move. Laniakea, whose name comes from Hawaiian and means immense sky or immeasurable horizon, was defined as the attraction basin that includes the Virgo cluster, the Great Attractor, and hundreds of other groups and clusters in a volume of space about 500 million light-years in diameter. The Great Attractor that figures in this structure is itself an anomaly that has intrigued astronomers for decades. Galaxies in a vast region of the sky, including the Milky Way, are moving towards a specific point with velocities that exceed what the expansion of the universe alone would explain. Something was pulling. Identifying what it was proved difficult because the region in question is, from the point of view of the Milky Way, behind the plane of the galaxy, in a direction where the dust and stars of the Milky Way itself obscure practically everything. The so-called zone of avoidance, the strip of the sky where the galaxy blocks our view of the distant universe, was hiding precisely the region of greatest interest. Radio astronomy techniques and observations in infrared wavelengths, which penetrate dust more easily than visible light, eventually allowed revealing what lay behind this curtain. The Great Attractor corresponds in part to the Centaurus cluster and associated structures, but more recent analysis suggests that the true center of attraction may be even further away, in a structure called the Shapley concentration or Shapley supercluster, one of the largest sets of galaxies in the observable universe, with a mass equivalent to tens of thousands of galaxies like the Milky Way. All of this, the filaments, the walls, the nodes, the voids, the clusters, the superclusters, the gravitational basins that encompass hundreds of millions of light years, is the result of quantum fluctuations amplified by cosmic inflation in the first instance of the universe, then sculpted by gravity over more than 13 billion years. The geometry of the large cosmic structure carries imprinted within it the signature of the initial conditions, the memory of the young universe still visible in the distribution of galaxies today. And here emerges a consideration that only becomes apparent when the totality of this structure is contemplated at once. All the patterns we described, the cosmic web, the clusters, the filaments, the voids, the hierarchy that goes from molecular clouds to superclusters of galaxies, are the result of gravity acting on density fluctuations in a mixture of dark matter, common matter, and radiation. The patterns are complex enough to fascinate any mind that contemplates them, but in a certain sense they are relatively well-behaved, progressive, hierarchical, reasonably predictable in their scales and geometries. There would be, however, something that fundamentally complicates this picture of increasing organization, something that does not align with the general trend of structure formation, that does not contribute to the grouping of matter into increasingly larger patterns, that acts not as an agent of order but as an agent of progressive and irresistible separation. The patterns we map exist despite this agent, or perhaps more precisely, the patterns we map are partly the historical record of the period in which gravity still dominated over this agent, before the balance began to tip definitively to the other side. This agent is dark energy. The name seems technical, almost clinical, and perhaps for that reason it does not immediately provoke the shiver it should provoke. Dark energy. Two words that cosmologists adopted for lack of something better, for lack of any real understanding of what they were naming. When one names something one does not understand, the name ends up being just a marker, a label stuck on a package whose content remains mysterious. Dark energy is precisely this, a name for our ignorance regarding a thing that, despite being ignored in its nature, is absolutely dominant in its effects. And the effects are extraordinary. Dark energy accounts for approximately 68 parts in every 100 of the entire content of the universe, not of all matter, but of all content, including matter and energy in all their forms. Dark matter, that enigmatic substance we saw in the previous part, that which forms invisible halos around galaxies and constitutes the framework of the cosmic web, this dark matter represents around 27 parts in every 100. All common matter, everything we have ever touched, everything we breathe, every star that has ever illuminated any eye, every rock, every ocean, every living being anywhere, all the matter we call baryonic, represents less than 5 parts in every 100. 5. Less than a 20th of the universe is made of what we consider real, of what forms our tangible reality. This should be disturbing, and it is. But the most disturbing thing is not the proportion itself, but what dark energy does with its dominant slice of cosmic content. It does not clump, it does not form structures, it does not collaborate with gravity to build galaxies or clusters or filaments. It does the opposite, it pushes. It is, in its essence, a negative pressure, a repulsion embedded in space itself, a tendency of the void to expand with its own energy. And this expansion is not linear. It accelerates. To understand what this means, it is necessary to go back to a moment that seems distant, but which is, in cosmic terms, relatively recent. For most of the history of the universe, gravity was the dominant force on large scales. The universe was expanding, yes, as it always has since the first instant, but this expansion was being slowed by the gravitational attraction of all the matter contained within it. It was like throwing a ball upwards. The ball goes up, but gravity continuously slows it down. For billions of years, the expansion of the universe was this process of gradual deceleration. Then, about 7 billion years ago, something changed. The expansion stopped slowing down, and it began to accelerate. This is the moment when dark energy took control. The reason it took control at this specific point is related to density. As the universe expands, matter, both common and dark, becomes less dense, the same amount of mass distributed over an increasingly larger volume. Gravity, which depends on the density of matter, therefore weakens as the universe grows. Dark energy, however, seems to behave in a completely different way. It does not dilute with expansion. Its density remains constant, or something very close to constant, regardless of the volume the universe occupies. This means that while gravity weakened with time, dark energy maintained its strength. And at the moment when the two balanced, dark energy was already at a growing advantage. From this crossover point, accelerated expansion became the permanent state of the cosmos. The discovery of this fact was in itself one of the most surprising moments in the history of science. In the late 90s of the last century, two independent groups of astronomers were studying type Ia supernovae, which are stellar explosions with known luminosity, a type of standard candle that allows measuring cosmic distances with precision. The expectation was that these measurements would confirm the deceleration of expansion. What they found was the opposite. Distant supernovae were fainter than expected, which meant they were farther away than they should be if the universe were decelerating. They were farther away because the universe was expanding faster than any model predicted. Saul Perlmutter, Brian Schmidt, and Adam Rees received the Nobel Prize in Physics in 2011 for this discovery. What they discovered was not just an interesting cosmological datum, it was the revelation that there is a force or entity or fundamental property of space that no one had predicted with rigor and that governs the final destiny of the universe. And to this day, we do not know what it is. The most accepted hypothesis is that dark energy is the energy of the vacuum. Quantum mechanics predicts that empty space is not really empty. It boils with quantum fluctuations, pairs of virtual particles that appear and disappear constantly, borrowing energy from the vacuum for time intervals so small that they are compatible with the uncertainty principle. This quantum vacuum would have an intrinsic energy, a cosmological constant, the famous lambda that Einstein introduced and later called his biggest mistake, and which today seems to be perhaps the most important quantity in modern cosmology. The problem is that when physicists calculate what the energy of the quantum vacuum should be and compare it with the value that observational cosmology requires to explain cosmic acceleration, the numbers do not match. They do not match by a margin that has no parallel in the history of science. The theoretical prediction exceeds the observed value by something between 100 and 120 orders of magnitude. This is, in practical terms, the largest discrepancy between theory and observation ever recorded in any field of human knowledge. Something fundamental is wrong either in quantum field theory or in cosmology, or in both. This abyss between calculation and observation is called the cosmological constant problem and remains unsolved. There are other hypotheses besides the cosmological constant. One of them is that dark energy is not a constant, but a dynamic field that evolves with time, something that cosmologists call quintessence, in reference to the fifth element of the ancients, that ether supposed to fill the skies beyond the moon. Quintessence would have a variable equation of state, with its ratio between pressure and density changing throughout cosmic history. This would allow acceleration to be different in the past and future, and could resolve some of the tensions between different cosmological measurements that persist currently. Another hypothesis is that our understanding of gravity is simply wrong on cosmological scales. Einstein's general relativity has been tested with enormous precision in the solar system and in binary neutron star systems. But on scales of billions of light years, perhaps gravity behaves in a way that the theory does not predict. Modified gravity theories, such as FR gravity or Dvali-Gabadadze-Parati theory, try to explain acceleration without invoking any form of dark energy, only modifying the equations that govern how space curves in response to matter. But regardless of which hypothesis is correct, the effect is the same. The universe is expanding faster and faster, and this acceleration has manifestations that we can observe, measure, and, in a certain sense, feel. The most direct manifestation is cosmological redshift. When light from a distant galaxy reaches us, it arrives stretched with longer wavelengths than it had when it was emitted. This happens because the space between us and that galaxy expanded during the time the light was traveling, and this expansion stretched the light along with it. The result is that light that was originally blue or violet reaches us shifted to the red. The more distant the galaxy, the older the moment it emitted that light, and the more space has expanded since then, and therefore the greater the redshift. This means that looking at the distant universe is looking into the past. When we observe galaxies 10 billion light-years away, we are seeing how they were 10 billion years ago. We are seeing the universe before dark energy assumed dominance, when gravity still controlled the dance. The galaxies we see at these extreme redshifts are young, irregular galaxies, often in the process of merging, forming stars at a frenetic pace. They are the building blocks of structures that did not yet exist. There is something profoundly melancholic in this observation. Every photograph of the deep universe is a letter from a time that has passed. The galaxies that appear in the deepest surveys of the Hubble Space Telescope or the James Webb Space Telescope, those reddish and irregular spots that seem so primitive and so full of energy, these galaxies probably no longer exist in this form. They grew, collided, merged with each other, generated generations and generations of stars, and today they are mature galaxies that we could, in theory, observe at a time of much lower redshift. But the very galaxies we see in the distant past are so far from us that we will never be able to visit them, or ultimately, even communicate with them, because here is the most silent and most disturbing manifestation of dark energy, the cosmological event horizon. This horizon is different from the event horizon of a black hole, although it shares the name and the central idea of a limit beyond which information cannot reach us. The cosmological horizon is an imaginary sphere around us, with a radius of approximately 46 billion light-years, which defines the edge of the observable universe. But within this observable universe, there is an even smaller subset, the sphere that defines which galaxies will be able to send us light that will eventually arrive here, even if we have to wait forever. With accelerated expansion, the space between us and galaxies beyond a certain distance is expanding faster than the speed of light. This does not violate special relativity, because it is not matter moving through space faster than light. It is space itself expanding, and there is no limit to the speed at which space can expand. But the practical effect is the same. Light emitted by these galaxies now will never reach us. They are, for all relevant purposes, beyond our permanent reach, and this limit is shrinking. As expansion accelerates, galaxies that are still within our reach horizon today will cross this limit in the future, on incomprehensible timescales, but which physics can calculate. Neighboring galaxies will move away beyond any possible contact. The local group, the set of galaxies to which the Milky Way and Andromeda and some dozens of smaller galaxies belong, will remain gravitationally united, because the internal gravity of the group is strong enough to resist expansion on such small scales. But the rest of the observable universe will slowly and then increasingly rapidly disappear beyond the horizon. There is something that resembles a form of cosmic loneliness in this image. Not loneliness in the human emotional sense, but loneliness in the structural sense. Islands of gravitationally bound matter, separated by vast oceans of acceleratingly expanding space, each island gradually unable to see or touch or interact with any other. The universe becoming an archipelago with increasingly distant islands, then an ocean without visible islands, then a void with increasingly faint memories that other islands existed. But this is future. Today the universe still exhibits the manifestations of the tension between gravity and dark energy in ways that we can observe with terrestrial and space instruments. One of them is the weak gravitational lensing effect. When light from distant objects passes through large concentrations of matter, such as galaxy clusters or filaments of dark matter, it is slightly deflected and the images of these distant sources appear slightly distorted. By statistically analyzing this distortion in surveys of hundreds of millions of galaxies, cosmologists can map the distribution of matter, including dark matter, and test models of how structure grew over time. These maps reveal that the growth of structures in the last billion years was slightly slower than expected, which is consistent with dark energy inhibiting the formation of new structures. Gravity still builds, but dark energy is gradually winning the battle, slowing the process, separating the ingredients before they can be incorporated into even larger structures. Another observable manifestation is the integrated Sachs-Wolf effect. Photons from the cosmic background radiation, that primordial light emitted 380,000 years after the Big Bang, have to cross gravitational wells created by large concentrations of matter. When dark energy is present and active, these gravitational wells are not static. They change while the photon crosses them. The photon enters a well, gains energy as it falls, but the well becomes shallower during transit because of accelerated expansion, and when the photon exits, it does not lose as much energy as it gained. The result is a small excess of energy that manifests as a correlation between the temperature of the cosmic background radiation and the distribution of galaxies. This effect has been measured and is consistent with models that include dark energy. Each of these observations, the redshift of supernovae, weak lensing, the integrated Sachs-Wolf effect, the general geometry of the universe measured by the cosmic background radiation, each of them points to the same conclusion. There is something we call dark energy. It represents the largest fraction of the content of the universe, and it is accelerating the expansion of everything. There is a way of thinking about this reality that is not just abstract, that can touch something more immediate in experience. Think of the space between your hands now. This space is expanding, not in a perceptible way, not in a way that any instrument we could build would be able to measure on this scale, because Earth's gravity and the cohesion of matter around us completely inhibit any expansion on such small scales. But the field that constitutes dark energy is there, present in every volume of space, including the space between molecules, between atoms, between subatomic particles. It is everywhere because it is a property of space itself, not a substance that occupies space, but something inherent to what space is. The reason we do not feel its effects on human or planetary or even galactic scales is that on these scales, gravity and other forces are so overwhelming that the expansive pressure of dark energy is completely negligible. But on scales where gravity dilutes in the distances between galaxy clusters, In the vast voids between cosmic filaments, their dark energy reigns without opposition. And what is in those voids is itself a story. Cosmic voids, the regions with very little matter that occupy most of the volume of the universe, are the domains where dark energy acts in its purest way. They expand faster than dense regions. They grow over time, gradually swallowing the regions of lower density around them. In them, the cosmic web has no threads. There is only space expanding in all directions, smooth and almost perfect in its uniformity. Cosmologists classify these voids in different ways depending on their size and depth. There are microvoids, small regions with tens of millions of light years in diameter, surrounded by filaments and sheets of galaxies. There are supervoids, the true abysses of the cosmic web, regions with hundreds of millions of light years in extent where the density of matter is a fraction of a few percent of the average density of the universe. And there are structures like the Boötes void, discovered in 1981, which is approximately 250 million light-years in diameter and contains only a few dozen galaxies where hundreds would be expected. For years it was considered anomalously large, a structure that seemed to defy structural formation models. Today we know that voids of this scale exist in abundance in the cosmic web, and they are precisely the regions where dark energy has exerted its power most completely. There is also the so-called CMB cold spot, a slightly colder region in the cosmic background radiation in the direction of the constellation Eridanus, which corresponds approximately to the position of a giant supervoid. This association between the cold spot and the void beneath it is another example of the integrated Sachs-Wolf effect, and it is one of the most direct pieces of evidence that dark energy affects the evolution of voids in a detectable way. Contemplating this from a more intimate perspective, it is possible to perceive that the universe we inhabit is a universe that exists in a kind of equilibrium that had its moment. For billions of years, gravity built, matter grouped, galaxies formed and grew and collided, and the cosmic web gained the structure we see today. This process still continues, but the engine that drives it is being gradually overcome. The order amplifier that was gravity has found its definitive counterweight in accelerated expansion. What we have today is a photograph of a particular instant in cosmic history, an instant in which structures still exist, in which filaments and clusters and superclusters are still visible, in which galaxies can still see each other at distances of billions of light years. But this instant is precarious. The balance between construction and separation, between gravity and expansion, between order and dissolution, is a balance that has already begun to tip definitively to one side. Every billion years that passes, the universe becomes slightly emptier, slightly colder, slightly more separated. Islands of matter remain, linked by gravity, but the oceans between them grow. And the growth is not arithmetic, linear, predictable like that of a plant that grows 1 centimeter per week. It is exponential, accelerated like a river that finds an increasingly abrupt slope. The more the universe grows, the faster it grows. The faster it grows, the more it moves away from the state that allowed communication between distant regions. The more it moves away from this state, the more the future that unfolds becomes different from the present we know. The equilibrium that seems stable today is, therefore, a pause in an irreversible transformation, a photograph taken in a fall. The cosmic web that we map with such care, that we describe with so many curves and filaments and nodes, is an artifact of a specific period in the history of the universe, a period that is ending slowly, but with all the certainty that physics can offer. What comes after this period, what exists beyond the edge of the universe in non-spatial but temporal terms, beyond the edge of time in which structure and order still define the cosmos, is something that cosmology begins to glimpse and that the deepest gaze can still reach. The transformation that comes after does not arrive as an announced event. It has no marked date on the calendar of any civilization. It emits no warning signal. It produces no perceptible tremor in the instruments that today orbit our planet or land on the desert in the southern hemisphere. It installs itself as if it had always been there, as if the entire universe were slowly realizing that the ground beneath its feet is not ground, but inclination, and that the inclination, however gentle it may seem at a given instant, inevitably leads to a state completely different from the one that existed before. The calm behavior of the cosmos, that state we described in previous parts as a web of filaments and nodes and voids, that arrangement that astronomers catalog with patience and that cosmologists model on supercomputers for years on end, this calm behavior depends on a very specific condition. It depends on dark energy continuing to act in the way it acts today. It depends on the cosmological constant remaining constant. It depends on the fabric of space not finding, at some point in its accelerated expansion, a threshold beyond which the rules of the game change irreversibly. And it is exactly here that cosmology begins to lose its tranquil tone and speak of possibilities that make physicists choose their words with great care, not for drama, for responsibility with what the calculations suggest. The first of these thresholds has a name that carries all its violence in a single extra syllable, the Big Rip. In English, the word also means tear, and that is exactly what models indicate as a possible destiny of the universe if dark energy is not constant but growing. If that which accelerates expansion continues to intensify over cosmic time, there will come a moment when expansion will not only separate galaxies from each other, as it already does today, but will begin to separate stars within the galaxies themselves. Then the stars themselves will dissolve, because expansion will act on scales smaller than gravity can keep united. Then the planets, then the molecules, then the atoms. Then, according to the most extreme versions of the model, the atomic nuclei themselves would be torn apart by the growth of space between the particles that compose them. What separates the universe we know from this destiny is a quantity that cosmologists call the equation of state parameter of dark energy, represented by the letter W. If this parameter is exactly equal to -1, dark energy is a pure cosmological constant. The universe expands forever, but in a way that gravitationally bound objects remain intact. If W is less than -1, dark energy is what is called phantom energy, and then the Big Rip is not just possible, it is inevitable. And the time left for it is inversely proportional to how much W deviates from -1. Current experiments measure W with impressive precision for human standards, but still insufficient to distinguish with absolute certainty between a universe that will end in rupture and one that will not. The error bars in measurements still encompass both scenarios. Every time a new galaxy survey is completed, every time a new crop of type Ia supernovae is catalogued, every time maps of cosmic background radiation are refined by another fraction of a percentage, physicists look at the value of W and check if it has crossed any threshold. So far, the data are consistent with -1. But consistent with is not the same as equal to. This distinction between consistent with and equal to is one of the most important that modern science inhabits. It is the space where dramatic possibilities still exist without having been discarded. It is the territory where the universe allows us to calculate alternative ends without yet telling us which one it chose. While you rest somewhere in a galaxy that our most powerful telescopes can still detect as a reddish point of light, a massive star is reaching the limit of what its core can sustain. It spent millions of years converting hydrogen into helium, helium into carbon, carbon into oxygen, and so on along the nuclear fusion chain that defines the existence of a star large enough to write this destiny in its own structure. Now the core has reached iron, and iron does not release energy when fused. Iron absorbs energy. The core stops producing the pressure that supported the weight of the entire star above it. In a fraction of a second that physicists measure in milliseconds, the core collapses. The matter falling onto it rebounds. A shock wave sweeps the star from inside out. What happens next is an explosion so bright that for days or weeks it surpasses in luminosity the entire galaxy that contains it. This explosion, the supernova, is not just a dramatic event, it is a laboratory. It is the occasion when the universe produces elements that no previous process managed to create. Gold, platinum, uranium, and dozens of other heavy atoms are forged in the extreme conditions of collapse and explosion, scattered into the interstellar medium, made available for gas clouds that will eventually form new stars and new planets. The heavy atoms in your body, in the metal you wear, in the electronics that transmit this sound, passed through at least one explosion like this before arriving here. But the supernova is not just a factory, it is also a clock. Because type Ia supernovae, those that involve the explosion of a white dwarf that has accumulated matter beyond a specific threshold, all explode with an intrinsic luminosity very similar to each other. They are standard candles. By measuring how bright they appear from afar and comparing with how bright they should be, cosmologists calculate distance with precision, and by measuring how their light was redshifted by expanding space, they calculate the speed at which they move away. It was comparing these two numbers in supernovae at large distances that physicists discovered at the end of the 20th century that the expansion of the universe is accelerating. It was this discovery that placed dark energy at the center of everything, and that opened the doors to the end scenarios that now occupy the most sophisticated models of cosmology. The acceleration of expansion is not a single and static event, it is a continuous process. And one of the most dramatic phenomena that it produces over time is what cosmologists call gradual cosmic isolation. As the universe expands more rapidly, the most distant galaxies begin to move away from us at speeds that exceed the speed of light. This does not violate special relativity because it is not that objects move faster than light in space. It is space itself that expands, carrying objects with it. The practical result is that light emitted by these galaxies will never reach us again. They have crossed the cosmological event horizon and disappeared from the observable universe forever. This horizon is not a physical wall, it is a causal limit. Once an object crosses the cosmological event horizon relative to an observer, that object can never again send information to that observer. Any light it emits from that point onward will be trapped in an expansion that runs faster than it, and as acceleration continues, the horizon does not stop swallowing galaxies. Over time, more and more galaxies will cross this threshold relative to us. The observable universe is shrinking, not in absolute size, but in number of objects with which we can exchange information. From a tremendously long time from now, measured in trillions of years, the visible universe for any civilization that still exists will be composed basically of the local group of galaxies, that gravitationally bound set to which the Milky Way belongs. Everything beyond this group will have moved away beyond the horizon. Astronomers of that remote future will have no direct evidence of the existence of other galaxies beyond their immediate neighbors. They will not have access to the cosmic microwave background, which will have been stretched beyond any detectable frequency. They will not have the data that we have today about the expansion of the universe. Completely different cosmological theories from ours will arise, and they will be consistent with the observations available at that moment. And they will be fundamentally wrong about the nature of the cosmos because the cosmos will have hidden most of its evidence. There is something profoundly disturbing in this idea, It means that the era in which we live, despite all our ignorance and all our limited instruments, is paradoxically privileged. The universe is still visible. Evidence of the big explosion is still within reach of our detectors. The cosmic web still exists and is still mappable. We are in a window of time in which cosmology is possible as a complete scientific enterprise. This window is closing, slowly but surely. The phenomena that emerge from the intense mode of accelerated expansion are not limited to the distant future. Some are happening now around us, on scales that human instruments are beginning to capture. Galaxy collisions, for example, are intensified by the dynamics of the expanding universe in a subtle way. Because nearby galaxies are still gravitationally bound to each other, and because expansion moves distant galaxies away but not nearby ones, groups and clusters of galaxies are gradually condensing. Galaxies within the same group approach, interact, collide, merge. Dark energy does not save them from this. Accelerated expansion actually concentrates gravitational action in local groups by removing from the scene everything that is outside them. The collision between the Milky Way and Andromeda, predicted to occur in a few billion years, is a local example of this process. When the two systems merge, the result will not be a catastrophe for individual stars, which are so separated from each other that most will not directly collide with any other, but interstellar gas, molecular clouds, star formation fields. These will be deeply disturbed. There will be violent bursts of new star formation. There will be stars expelled to orbits that will take them into the intergalactic void. The supermassive black hole in the center of each galaxy may eventually merge with the other, releasing gravitational waves of colossal amplitude that will propagate through space-time for billions of light years. Gravitational waves are one of the most dramatic phenomena that the intense mode of the cosmos produces, and also one of the most recent to be directly detected by human instruments. When two massive objects orbit each other and gradually approach, they disturb the fabric of space-time, creating ripples that travel at the speed of light in all directions. These waves carry energy, and by carrying it, they remove energy from the system that generated them, causing the objects to approach even more, which generates even more powerful waves, which accelerates the approach even more, in a feedback cycle that ends in the catastrophic fusion of the two bodies. The detectors that humanity has built to capture these waves are works of engineering that border on the absurd in terms of sensitivity. They are capable of measuring variations in the length of an arm of several kilometers that are smaller than 1,000th of the diameter of a proton. To give an idea of what this means, a proton is already immensely smaller than an atom, and an atom is already immensely smaller than anything the human eye can discern. Detectors observe distortions of space-time that happen billions of light years away, when two black holes that each had tens of times the mass of the Sun merged in less than a second, releasing more energy than all the stars in the observable universe together release in light during that same second. When physicists describe these events, they are describing the most violent phenomena that exist in the observable universe, and they are describing something that is not exceptional. Black hole mergers happen somewhere in the universe with a frequency that detectors already allow estimating. The universe is constantly agitating at frequencies that we have just learned to hear. Gravitational wave astronomy is a new sense that humanity has just developed, and what it is perceiving is that the cosmos in intense mode is much noisier than the cosmos that optical telescopes describe. But black holes are not just products of individual stars that collapsed. Supermassive black holes that live in the center of galaxies have masses that reach billions of times the mass of the Sun, and their origin is still one of the most intriguing open problems in astrophysics. How did such massive objects form so early in the history of the universe? when the universe was still too young to have had time to build these masses through normal processes of accretion and fusion? Data from telescopes observing the young universe show quasars, active galactic nuclei of extraordinary brightness, fueled by supermassive black holes, existing only a few 100 million years after the Big Bang. Cosmology still does not have a complete answer for how these monsters form so quickly. What is clear is that when a supermassive black hole is in an active phase of accretion, when it is swallowing gas and stars and matter in enormous quantities, what happens in its vicinity is one of the most energetic spectacles in the universe. The material falling towards the black hole does not fall in a straight line. It forms an accretion disk, a flattened structure where matter spins at speeds that reach significant fractions of the speed of light, heating up to temperatures of billions of degrees and emitting radiation at all frequencies from radio to gamma rays. Part of this energy is channeled by the intense magnetic fields of the system into relativistic jets, columns of heated plasma that are launched in opposite directions to the plane of the disk at speeds close to that of light, extending over distances that can reach millions of light years. These jets, when pointed in the direction of Earth, are what we call blazars, and they are the most luminous objects we can observe in the universe. They are cosmic beacons that illuminate epochs and distances that would otherwise be invisible to us. Every photon that arrives from the most distant blazars has traveled a journey of billions of years before hitting the mirror of a telescope or the detector of a gamma-ray camera in orbit. It carries information about the state of the universe when it had a fraction of its current age. Humanity has built an entire fleet of observatories to capture these messengers. Telescopes on the ground, telescopes in orbit, particle detectors buried in the ice of Antarctica or scattered across the Atacama Desert, instruments that float in stratospheric balloons, detectors that observe the sky at frequencies that the human eye could never perceive. Each of these instruments is a collective effort of generations of researchers trying to wrest information from the cosmos, trying to understand not only what exists, but what will exist and what existed, trying to trace the complete curve of the history of the universe from its beginning to its probable end. And what all these instruments together are confirming, with a consistency that leaves little room for alternative interpretation, is that the universe is in a state of accelerated transformation, that the rhythm of change is increasing, that the dramatic phenomena we described, black hole mergers, relativistic jets, galaxy collisions, star formation bursts, supernova explosions, all this happens within a cosmological context that is itself transforming more rapidly than any of the structures it contains. It is like describing waves with richness and detail without realizing that the entire tide is changing direction. The waves are real, they are measurable, they are beautiful and violent and full of pattern, but they are expressions of something greater that governs them, and that, by being greater, changes more slowly and therefore seems stable when observed on human time scales. The drama of individual phenomena, the supernova that explodes tonight, the pair of black holes that merge in a distant galaxy, the quasar that illuminates the young universe, these events are at once independent occurrences and local expressions of a process that encompasses them all. None of these phenomena happens in true isolation. Every supernova explosion pollutes the interstellar medium with elements that will change the chemical composition of the next molecular clouds. Every black hole merger alters the gravitational field of the surroundings in ways that influence the orbits of stars at immense distances. Every relativistic jet heats the intergalactic gas of an entire cluster, suppressing the formation of new stars for periods lasting hundreds of millions of years. And all this happens within a universe in which dark energy is reorganizing the distances between actors, changing the rules of who can interact with whom, silently drawing the limits of what is still possible and what has already passed beyond reach. What makes this cosmic fabric so difficult to contemplate is not its greatness, but its intimacy. Every region of the universe is in constant conversation with surrounding regions, exchanging matter, energy, gravitational information, radiation. There are no dividing walls between the phenomena we call local and those we call cosmological. What happens in the nucleus of a galaxy resonates with decreasing intensity but never null to the edges of the filament in which it is inserted. And this filament, in turn, is just a nerve of an even larger structure, which is itself immersed in an environment whose properties are defined by the global geometry of space-time. The most intimate partner of any energetic process in the late universe is dark energy. It does not act like other forces, it does not push or pull any specific object, it has no target, it has no center. What it does is more subtle and deeper. It alters the rate at which distances grow. By doing so, it changes the efficiency with which gravity can group matter. On scales smaller than a few tens of millions of light years, gravity still dominates, and galaxies, clusters, and filaments maintain their internal cohesion. But on larger scales, dark energy wins this dispute, and the large voids between filaments grow in a way that no local gravitational process can reverse. The universe organizes itself, therefore, into islands of complexity separated by increasingly vast oceans of almost nothing. Within these islands, feedback cycles are the mechanism that regulates everything. A feedback cycle is a situation in which the output of a process feeds back into the input of that same process, amplifying or moderating what happens next. In the cosmic context, these cycles operate on timescales that make any comparison with what we call long-term in human experience absurd. Consider the cycle between star formation and chemical enrichment of the interstellar medium. A cloud of primordial hydrogen and helium collapses and forms stars. These stars live, process heavier elements in their cores, and eventually die, scattering carbon, oxygen, iron, silicon, and dozens of other elements into the space around. This enriched material mixes with the gas that still exists in the galaxy, and the next molecular clouds that form from this gas have a different composition. They cool more efficiently, because heavy elements emit radiation more easily than pure hydrogen, and this more efficient cooling changes the typical mass of the stars that are born. The feedback was completed. The product of the previous process altered the conditions of the next process. This specific cycle took approximately 2 billion years to complete its first turn in the primitive universe, and continues to repeat with variations to this day. Each iteration leaves a chemical signature in the interstellar gas that astronomers can measure by looking at the light spectrum of old stars and comparing with that of young ones. Stars of the so-called population 2, formed when the universe was between 1 billion and 3 billion years old, contain much fewer heavy elements than the Sun. Population 1 stars, like the Sun, which were born later, carry in their own bodies the record of all previous generations of stars that lived and died before them. The iron circulating in our blood was forged in at least one supernova that occurred before the formation of the solar system more than 4.5 billion years ago. The chemical feedback of the cosmos is literally constitutive of what we are. But there is a second feedback cycle that operates in parallel and interacts with the first, the cycle between the central black hole of a galaxy and the gas that feeds it. When a galaxy accumulates enough gas in its center, the supermassive black hole begins to feed intensely, and the jets and winds that this activity produces heat the gas around, preventing it from collapsing into new stars. This heating can last hundreds of millions of years. During this time, the star formation rate of the galaxy drops drastically. With fewer stars forming, there are fewer supernovae enriching the gas, and with the gas heated and dispersed, the black hole itself loses its fuel and enters dormancy. When the black hole sleeps, the gas begins to slowly cool again, on timescales of a few billion years, and the cycle can restart under slightly different conditions. This cycle, called by astronomers as active galactic nucleus feedback, is today considered the main mechanism that explains why the most massive galaxies in the universe stopped forming stars long before smaller galaxies. Giant elliptical galaxies, like those that inhabit the centers of large clusters, contain black holes with masses reaching a few billion solar masses, and their jets are energetic enough to heat the gas of the entire cluster, not just the galaxy itself. The heat deposited by these jets can be sufficient to keep the gas hot for entire geological eras, suppressing star formation in dozens of neighboring galaxies at the same time. A single object, a dormant black hole in the center of a cluster, alters the destiny of a structure that contains hundreds or thousands of galaxies. Feedback operates on scales that have no convenient name in everyday experience. In the short term, which in the cosmic context can mean anything between a few tens of thousands of years and a few million years, the universe seems static to any observer who existed within it. A civilization that lived for 1,000,000 years would observe the sun slightly brighter at the end of that period than at the beginning, would notice some stars that disappeared and some new bright spots where there were previously dark clouds, and would perceive that neighboring galaxies seem very slightly more distant. Changes are happening, but at rhythms that make it difficult to distinguish them from the immobile. On scales of hundreds of millions of years, the panorama changes radically. The spiral arm of a galaxy completes almost a full turn around the galactic center in about 250 million years, in the case of the Milky Way. Stars that today share the same cosmic neighborhood will have dispersed completely in this period, and the Sun will be on the other side of the galaxy relative to its current position. Supernovae will have occurred in the neighborhoods at distances small enough to alter the chemistry of the gas cloud that will eventually form the next solar systems in the region. The pattern of filaments of the cosmic web will have modified perceptibly, with some filaments thickening as they gain matter and others becoming more tenuous. On scales of billions of years, the universe enters a qualitatively different regime. Entire galaxies merge, transforming delicate spiral structures into irregular ellipticals. The gas that previously fed star formation is being consumed or expelled, and galaxies age, becoming increasingly dominated by old and red stars. The Sun itself will complete its life cycle in about 5 billion years, expanding into a red giant before collapsing into a white dwarf that will cool passively for the time remaining to the cosmos. Andromeda, today 2.5 million light-years away, will have initiated its collision with the Milky Way in about 4.5 billion years, and in 6 or 7 billion years the two galaxies will have merged into a single elliptical structure that some astronomers have already informally called Milkdromeda. This differentiated behavior between timescales reveals something fundamental about how complex systems evolve. They have memory. The current condition of the universe carries information about all previous states, and small differences in initial conditions propagate in ways that become increasingly impossible to track with the passage of time. It is here that sensitivity to initial conditions enters as a theme, not only scientific but philosophical. Modern physics carefully distinguishes between what is deterministic and what is predictable, and this distinction is deeper than it appears at first glance. A system can be completely deterministic. in the sense that each future state is causally determined by the present state and yet be fundamentally unpredictable in practice, because any infinitesimal imprecision in the measurement of the present state amplifies exponentially over time. This behavior, which mathematicians call sensitivity to initial conditions, was formalized in the context of chaos theory, but its effects permeate the universe on scales that go far beyond the systems we normally associate with chaotic behavior. The trajectory of a star within a globular cluster, for example, is technically determined by the gravitational forces exerted by the other hundreds of thousands of stars around. But simulating this trajectory with precision for more than a few 100 million years becomes impossible in principle, not just in practice, because the inevitable rounding errors in any computational representation amplify without limits. And on the scales of the universe as a whole, where interactions between billions of galaxies add up over billions of years, the horizons of significant prediction become ridiculously short compared to the timescales we are contemplating. This is not a failure of science. It is a revelation about the nature of reality. The universe is richer than any model we can build of it, not because there are gaps in knowledge that we will someday fill completely, but because the very structure of complexity prevents perfect prediction without destroying the limits that define the observer. To predict with absolute precision the state of the universe in 1 billion years, we would need a model as detailed as the universe itself, which is another way of saying that the only perfect model of a thing is the thing itself. And here we find something that deserves to be contemplated calmly. Science is not an attempt to replace the universe with a simpler map, but an art of finding the patterns that persist despite the irreducible complexity of the substrate. When an astronomer discovers that the mass of a central black hole correlates with the velocity dispersion of the stars in the bulge of the galaxy that hosts it, this correlation is not a coincidence nor an artifact of how we measure things. It is a footprint left by a feedback process that operated for billions of years, simplifying the initial diversity of conditions into a relationship that we can write in a single equation. The emergent simplicity in a chaotic system is a gift that the cosmos gives us, and recognizing it is an act that combines rigor and awe in equal proportions. What is beautiful in this structure is not just that the universe is large or old or energetic. What is beautiful is that it is at once completely beyond what we can intuitively grasp and still surprisingly accessible to ordered thought. The equations that describe the dynamics of the filaments of the cosmic web were written on blackboards by beings that evolved to hunt in African savannas. There is something profoundly disconcerting in this, an asymmetry between the humble origin of our brains and the amplitude of what they can model. And this disconcert is not a weakness of the scientific method. It is evidence that something in the universe has a structure that resonates with the type of order that minds like ours can recognize. The connected systems of the cosmos, the filaments that exchange matter with clusters, the black holes that regulate the birth of stars, the supernovae that poison and fertilize the interstellar medium at the same time, the gravitational waves that arrive silently from mergers occurring billions of light years away, compose a score that no ear can listen to at once. But it is a score, not noise. There is rhythm, there are motifs that repeat in variation, there is a logic that crosses scales. The molecular cloud that collapses and the supercluster that fragments obey the same principle of gravitational instability, only in masses and times different by factors of trillions. The jet of a quasar and the wind of a young star are the same type of phenomenon, fueled by the same physics of accretion, only in energies different by equally vertiginous factors. This recurrence of patterns between scales is an invitation to a question that science touches at its limits, but that goes beyond what any set of data can answer directly. If the same principles reappear on such different scales, if gravity is the same law that binds a moon to its planet and a filament to the cosmic web, if the instability that fragments a gas cloud and creates stars is the same instability that fragmented the quantum fluctuations of the primitive universe into seeds of galaxies, then perhaps the multiplicity of phenomena we described throughout this journey is, at bottom, the expression of a much smaller number of fundamental principles than superficial diversity suggests. It is not a new idea. Physicists and philosophers of nature have dreamed of it for centuries. But what is new is the amount of evidence that now points in this direction, coming from domains as different as cosmology, particle physics, stellar astrophysics, and information theory. The threads that connect these areas are real, they are not metaphors. The same fundamental constants of nature determine the internal structure of atoms and the curvature of space on a large scale. The equations that describe the entropy of a black hole have the same mathematical form as the equations that describe the entropy of a gas in a box. Something unifies these disparate appearances at a level deeper than any of these phenomena individually. This sensation of proximity to a unifying principle, without it being yet completely articulated, is perhaps the most characteristic experience of studying the cosmos at its most extreme edges. It is not the satisfaction of a solved problem, nor the frustration of an intractable problem. It is something more like recognizing a word on the tip of the tongue, feeling that the structure of what is sought is somehow present in the mind before the verbal form to express it exists. The universe seems to be saying something that has not yet finished being said, and we, in our strange position of stardust that learned to ask questions, are listening with all the attention we are capable of. The rhythm of all this begins to slow down as we move away from the whirlwind of events and begin to contemplate the structure that contains them. The black hole mergers that occur billions of light years away have their own urgency, but viewed from a step back, this urgency dissolves into the silence of intergalactic space. The waves they produce travel for eons before finding anything that detects them. The universe has infinite patience with its own processes, and there is something profoundly calming in realizing that the cosmos is in no hurry. Every event, however violent it is on its local scales, is just a moment in a sequence that extends over a time so vast that the word vast cannot reach what we mean by it. And in this slowness contemplated with calm, an intuition begins to emerge that is difficult to name without deforming it. Behind all the complexity of interconnected systems of feedback cycles that operate over billions of years, of sensitivities to initial conditions that make prediction humble, of patterns that repeat on scales impossible to imagine together, there is something that is not any of these phenomena individually, but that somehow encompasses them. It is not a force, it is not a particle, it is not an equation, at least not in the way we use these words so far. It is something more fundamental than any of these instruments of description, something whose nature is precisely at the limit of what human language and thought can approximate without losing precision. This something still has no consensual name, but its shadow is everywhere, and learning to recognize it is the next step of the journey. This something that resonates behind all phenomena, that is neither force nor particle nor equation, has a particular quality that deserves to be inhabited with patience before being named. It is the quality of being simultaneously structure and movement, continent and content, map and territory. When we look at the edge of the universe, at that impossible frontier that recedes at the same speed we try to reach it, we are looking at something that challenges the division between observer and observed. The universe we try to describe is the same universe that produced us to describe it, and this is not a minor philosophical curiosity. It is perhaps the strangest and most beautiful thing that exists. To reach the deepest dimension of what it means to exist a border or an absence of border in the cosmos, we need to descend to the level where everything begins. Not the beginning in the sense of an inaugural instant, but the beginning in the sense of foundation. The matter that forms the most distant galaxies, those that are already beyond the cosmic event horizon and whose images will never again reach our telescopes, is composed of the same elements that form the planet where you rest now: hydrogen, helium, carbon, oxygen, iron. The table of elements does not change at the edge of the observable universe. The same forces that keep an electron in orbit around the nucleus here keep that electron in orbit at any point of the cosmos accessible to our observation. This compositional uniformity is extraordinary because it tells us that there is no chemical border in the universe. There is no place where matter changes nature, where atoms are made of something else, where the rules governing molecular bonds become other rules. And this uniformity points to something even deeper. Physical constants, those numbers that determine the strength of gravity, the speed of light, the charge of the electron, seem to be the same in all directions and at all distances we can measure. When we study the light of quasars that traveled for billions of light years to our detectors, the spectral structure that this light carries reveals the same atoms, the same electronic transitions, the same processes that we observe in the laboratory. The universe, in its most intimate composition, is profoundly monotonous in the most beautiful possible sense of that word. It is a theme with infinite variations, but the theme never changes. The feedback processes that maintain this coherence are astonishing in their elegance. When a star is born, it is born because gravity compressed a cloud of gas to the point where pressure and temperature in the core activate nuclear fusion. Fusion releases energy. This energy creates a pressure that opposes gravity, and for a few billion years, a star like the Sun lives in this dynamic equilibrium, in this conversation between two processes that limit each other. Gravity wants to compress. Fusion resists. Neither completely wins while the fuel lasts. This is a negative feedback cycle in the technical sense, a stabilizing mechanism that keeps the system in a functional state long enough for all the complexity that depends on starlight to exist. Without this feedback balance, stars would be either instantaneous flashes of collapse or eternal clouds that never come to shine. But there is also feedback that amplifies, that does not stabilize, but scales patterns in unpredictable ways. When the young universe was only a few 100 million years old, the first density fluctuations in dark matter began to attract more matter. More matter meant more gravity. More gravity attracted even more matter. This process of gravitational amplification transformed minute, almost imperceptible fluctuations into immense filaments of matter and then into galactic clusters. The large-scale structure of the cosmos we observe today, this web of filaments separated by immensely silent voids, is the direct result of a positive feedback that operated over billions of years from variations that were, in the beginning, smaller than we can imagine. The universe amplified its own whispers until they became the roar of billions of galaxies. This game between stabilizing feedback and amplifying feedback is present at all scales we encounter on this journey. In black holes, which consume matter but also launch jets that suppress star formation in host galaxies, limiting their own growth in a way we do not yet fully understand. In the cosmic microwave background radiation, which is both the record of a past amplification and the map of a stabilizing uniformity. In the life cycles of stars themselves, which create the heavy elements that make the chemistry of life possible, launch these elements into interstellar space when they die, and with this feed the formation of new stars richer in elements. The universe recycles itself in cycles that cross unimaginable timescales. The systemic vision that emerges from all this is of an integration that goes far beyond what the word integration normally evokes. An integrated system, in the usual sense, is one where parts communicate and influence each other. But the universe is not just a system where parts communicate. It is a system where there is no clear boundary between what is part and what is whole. A galaxy is part of the galactic cluster, which is part of the supercluster, which is part of the filament, which is part of the large-scale structure, which is part of the observable universe. But the observable universe is not a part of something larger in the same way, because it defines the horizon beyond which causality, at least the causality we know, ceases to operate. And at the same time, each galaxy contains within itself billions of stars that are systems. Each star has planets that are systems. Each planet has atmospheres and oceans and continents that are systems. And on some extraordinary planets, there are living systems that create systems of thought that try to apprehend the whole. This recursive nesting of systems within systems is not just a convenient description, it is something that seems fundamental to the way the universe organizes itself. And this leads us to the heart of emergence, that phenomenon where simple rules, applied repeatedly in local interactions, produce patterns of complexity that were not obviously written in the rules. Newton's gravitational equation is relatively simple. It describes the force between two bodies as proportional to the product of their masses and inversely proportional to the square of the distance. But when this simple rule is applied to billions of particles interacting simultaneously, what emerges is the web-like structure of the universe, the whirlpools of spiral galaxies, the orbits of planets, the tides of oceans. Nothing in this equation says form a spiral galaxy, but spiral galaxies form. Emergence is not magic, but it often seems so because we are accustomed to thinking that the complexity of an output must be present in some way in the input. When we see something very complex, we look for an equally complex cause. But nature repeatedly surprises us with the ability to generate profound complexity from rules of disconcerting simplicity. The equations of general relativity are elegant, and from them emerge not only the trajectory of planets but black holes, gravitational waves, the expansion of space itself. The laws of thermodynamics are few and clear, and from them emerges the entire direction of time, all the inevitability of cooling and dissolution that will eventually find even the stars. And here is the threshold where the journey deepens to its most silent layer. At bottom, the edge of the universe is simply the limit of what can be reached by relationship. This is the central idea, the unifying principle that encompasses everything we traversed together on this journey. The observable universe is not a crystal ball with a wall. It is the set of everything with which light has had time to establish a relationship since the beginning. The edge is not a boundary in space. It is a boundary in the possibility of contact, and this fundamentally changes what it means to ask what exists beyond it. When we contemplate the cosmic event horizon, we are contemplating not a wall but the maximum reach of any influence that could have reached us. The galaxies that exist beyond this horizon exist as much as those we see, but they have never exchanged information with us. They never could. The universe, from this perspective, is the totality of possible relations, and the edge is simply where these relations end for us, from here, now. This reconnects every element of our journey to a single thread. The quantum fluctuations of the primordial universe, which we studied in the first parts of this journey, were the first relations, the first encounters between energy and possibility. Nucleosynthesis, the formation of the first atoms, was the beginning of chemical relations that would give rise to all material complexity. Galaxies are structures of gravitational relation between billions of stars over billions of years. Nebulae where new stars are born are the result of relations between stellar winds, magnetic fields, and shock waves that conspired to compress gas to the point of ignition. Black holes, which seem the anticlimax of all relation because they swallow everything, are actually the points where gravitational relation reached its maximum intensity, where space and time curve so much that even the relation between cause and effect transforms into something we can barely describe, and the accelerated expansion of the universe, that disturbing discovery that emerged from observations of distant supernovae, is the story of how the space between relations is growing faster than new relations can be formed. The universe is, in a very precise sense, becoming progressively lonelier. The galaxies that today are part of our local group, which gravitationally belong to us and to whom we belong, will remain with us. But the rest of the cosmos is moving away, and there will be a time, in trillions of years, when any civilization that eventually exists in the Milky Way will see nothing beyond the local group. Everything else will have receded beyond the cosmic event horizon. The observable universe of that distant future will be much smaller than ours, not because the cosmos has shrunk, but because possible relations will have decreased. This perspective of relations as the fundamental fabric of the cosmos resolves in a gentle way a paradox that the edge of the universe carries. If we ask what exists beyond, the answer is not nothing, nor something we cannot reach. The answer is, what exists beyond is what has no relation with us. It is not an absence of being, it is an absence of contact. And these are fundamentally different things. The universe beyond the horizon is as real as this one, but its reality has never crossed our path and ours has never crossed its. There is something profoundly comforting in this idea if we allow ourselves to inhabit it with calm. It means that the universe we know is exactly the universe of which we are part. It is not a limited window to something greater that we are missing. It is the set of everything that constitutes us, of everything that contributed to making this moment, this thought, this approaching rest possible. Every photon that reached Earth and heated the primitive oceans, every supernova that seeded space with the carbon atoms that form our body, every density fluctuation that generated the galaxy that harbors our sun, all these relations are within the horizon. All were part of the chain of context that brought us here, and now the journey begins to dissolve, not into confusion but into clarity, a soft clarity like the moment when eyes stop actively searching and simply receive the light that is already present. The universe has no edge in the sense that a room has walls. It has horizons, and horizons are always relative to who looks, from where they look, when they look. You are part of the web of relations we call the observable universe, not metaphorically, chemically, gravitationally, electromagnetically. The atoms that compose your body were forged inside stars that died before the sun was born. The water circulating in you carries hydrogen that is almost as old as the cosmos. You are a local concentration of information and complexity that the universe created for itself over billions of years of increasingly intricate relations. While you rest, the universe continues its silent expansion. Galaxies move away from each other with a slowness that no word can describe. Stars complete tiny fractions of their orbits around galactic centers. Gas clouds in distant nebulae condense very, very slowly towards the point where one day they will burn with new light. Black holes wait with the patience of things that do not age in the same way as everything around. Everything continues, and you are safe within this continuing. Your body knows how to rest. It knows how to deliver thought to silence. Every breath you take is the universe breathing through you. And there needs to be no effort in this, just the natural rhythm, the flow that exists without you needing to sustain it. You are safe. The cosmos that formed you does not abandon you while you sleep. The gravity that keeps stars in orbit also keeps you gently on the surface of this earth. You do not need to hold on. You are already sustained. While you rest, the universe continues its patient expansion. its dance of galaxies in silent dialogue, its cycles of birth and dissolution that cross time scales beyond any count. Everything is in order. The constellations that our ancestors learned to name continue in their relative places. The moon completes its arc. The tides obey their ancient conversation with the gravitational field. The processes that sustain life on this planet continue without needing any attention from you. You can rest completely. The universe takes care of you in the only way the universe knows how to take care, keeping physical constants constant, keeping atoms cohesive, keeping the heat of the sun arriving tomorrow as it arrived today. You are part of this. You always have been. Long before you existed as you were already the stardust that would one day meet in this form. And when this form dissolves, as everything dissolves, you will return to being part of something broader. There is no loss in this. There is only the continuous dance of relations, always recomposing in new patterns. For now there is only rest. There is only the breath that enters and exits without effort. There is only the lightness of not needing to arrive anywhere. The end of the universe, if it exists, is infinitely far away. There is time, there is space. There is enough silence for everything that needs to happen, including the dream that is arriving. Let thoughts dissolve like galaxies receding beyond the horizon, not with sadness, just with the natural smoothness of things that follow their path. You are at peace. The universe continues its silent dance and we rest in its embrace. Thank you for walking with me tonight. Sleep well.